Okay, so we have seen that the Fourier transform of the derectified signal xs of t is equal to this quantity, which can also be written as a sum of multiple copies, infinite copies of the original spectrum of the continuous signal. So I get this sequence of copies of the continuous signal x of t. And then, I can use the inverse Fourier transform and recover the original derectified signal using this integral, okay? But now what we would like to do is instead, we are interested in recovering only the discrete signal, which contain which are the values of the continuous signal sample at every ts seconds. So we can do that by means of convolution, because, for example, if I take this windows, which is a center at NTS, automatically I will get the value of the sampling at NTS of the original signal. Indeed, as I wrote here, x sub n is going to be equal to the integral between minus infinity and infinity of the derectified signal times the window that we need to define shifted at NTS in delta t. Okay? And this window is pretty easy to define, because in this case, it is a box function. Okay? So, but that is our starting point. So, given this, it will be easy now to derive this is simply the convolution between x of t and the window, but computed at t equal NTS. Okay? And of course, it's the only value that will survive, because all the other values at any time t are 0. So let's study more in details this part, okay? And the important thing is to realize that in order to recover the discrete signal, we need to convolve the derectified signals with a special window, okay? And there are you will see that there are infinite choices for this window W. Okay, let's see this more in details. Okay, so if this is my derectified signal, which is sample every ts, xs of t equals sum minus infinity to infinity of the discrete signal t minus nts. Okay? And we can recover the original signal xn of t by convolving the rectified signal with a special window that I now define it, and then evaluate these results, this convolution at t equal nts. Now, the choice of the window, so this is going to be equal what? It's going to be equal simply to the integral between minus infinity and infinity of x of f of t w t minus nts in delta t. Okay, that's how. But now, in order to do this, we're going to assume basically that we need to have a window that has the following properties. For it. Here I'm going to have n plus 2 ts. Here I'm going to have the same 2 n minus 2 ts. So in order to write this expression, this is basically Wt minus NTS. We want this window needs to have the following property. First of all, Wt is symmetric. So which means Wt equal W of minus T. Then we want what? We want to make sure, of course, that the area of the window is positive. It's not infinity. And then we're going to impose that W at 0 is equal to 1. But also we want that W at any other time t equal n ts is going to be 0 with n different than 0 for any n different than 0. So this is enough for as long as we pick any window which satisfies these properties, we are able to recover the discrete signal by means of this convolution. And from going from here to here, I already made an extra step because I already assumed that Wt is symmetric, okay? Because in reality, the original signal is, this convolution is xs of t, W NTS minus t in delta t. Okay, but here I already I assume that Wt is symmetric. Okay, so that's why I can swap it and rewrite it in this form. Of course, if I apply this convolution at any other time different than NTS, basically I'm gonna get 0. And okay, nice. So we have a way to recover the discrete signal from the Diractified signal. So let's see now if we can now rewrite this expression in terms of the discrete time Fourier transform. So x of n is equal to the Diractified signal convolved with W of t, and then computed at t equal NTS. Okay, and this the window that we choose has to be Wt symmetric. W at 0 has to be equal to 1. W at NTS has to be equal to 0 for any n different than 0. And of course, the integral of the window has to be less than infinity. So we want a bounded window. And there are infinite choices of this window, okay? Because, and now we're going to see now which are these choices, okay? So of course now this I can write it as the convolution integral of xs of tau W t minus tau in d tau. But then I need to compute this at t equal NTS. So this is equal to the integral minus infinity to infinity of xss of tau W NTS minus tau in d tau. Okay? And so at the end of the day, I can rewrite it as I can exploit the symmetry of my Windows function And so I can rewrite it as integral minus infinity to infinity excess of tau w tau minus anti-s in d tau. Okay? And this automatically will give me the discrete signal, and I have an infinite choice of windows. Okay? Which will recover the discrete signal. Let's pick up 2 examples of this, and let's see which one are more convenient. Let's see. I can, for example, the natural choice will be the following, the one that I already show in the previous slices. Here I have my discrete signal. And I take as a window a box function. Okay? This is my first choice. And so W of t is equal to u of t plus ts divided by 2 minus u t minus ts divided by 2. And of course, we know what is the Fourier transform of this signal, of this window. We already derived it in previous lectures. I'm not going to redo it here. W of omega is equal to Ts times sine of omega Ts divided by 2 divided omega Ts divided by 2. So this is the Ft of Wt that will be helpful in the next slides. And indeed, this will do the job. But I can also consider another window. This is the first choice. I also have this other choice. I still have my discrete signal at nts n minus 1 ts and n plus 1 ts. So here I have the discrete signal, and I can choose the sinc function. I can choose as a window Wt, this is my B choice, Wt equal sine of pi t over Ts divided pi t over Ts. Is right? Because this function now is gonna be 1 at 0 and then 0 at all the others values, okay? So these are 2 choices these are 2 windows which will return the discrete signal from the derectified signal, okay? Of course, the Fourier transform of this guy, of the sinc function, is pretty easy because it's the dual of this. So we're gonna get a box in Fourier domain. The main point here is that they are they are there are infinite ways to choose the window, and you will still recover the same signal and the discrete signal. And here there are two choices: the box and the sinc function. Okay, let's see. I mean, what is the correspondent? Let's see what we can gain from these two choices. Okay. So let me summarize what we did here. We can write x. The discrete signal can be written as the convolution between the directified signal and a special window W computed at t equal nts. And this can be written as the integral minus infinity to infinity of the directified signal W of nts minus tau in d tau. But of course, we have two choices of W. We can do it. Let me do it here. Here we have nts, n plus 1 ts, n plus 2 ts, n plus 3 ts, n minus 1 ts, n minus 2 ts, and let's do another one here, n minus 3 ts. So here we get our nice continuous signal, x of t, and then here we sample it by multiplication with a Dirac train, and we get our nice directified signal. And then I can choose, for example, this window. Or I can choose the sinc function, basically. Okay, so we have two choices. Let's call WA of t, and this is WB of t. Okay? And the important thing is that WT symmetric. W at 0 is equal to 1. W at the other sampling time is equal to 0 for each n different than 0. And of course, the area has to be bounded. As long as I satisfy these criteria, I can recover the original discrete signal using this convolution. Okay? And of course, WA of t is simply u of t plus ts divided by 2 minus ut minus ts divided by 2. The other choice with the sinc function, it is the sine of pi t over ts divided pi t over ts. And these two different windows, they will return me the original discrete signal. Of course, if I want to recover the entire signal, the continuous signal, the right window to choose is going to be the sinc window. Okay, but here we're all interested in the discrete values, and so you can choose any windows. Let's see what is the impact on the Fourier transform when I choose these two different windows. Of course,